Hello everyone, this is 17th lecture, and in this lecture we shall discuss about the applications of Gauss theorem. And the first application of Gauss theorem which is included in our syllabus is electric field intensity due to uniformly charged infinitely long straight wire. So here we consider an infinitely long straight wire and we consider a part of L length of the wire and Q is the corresponding charge of the wire and a distance r, P is the point where electric field intensity to be calculated. To calculate the electric field intensity, first of all we consider the length element, means this whole part of the wire is divided into small length elements, and we consider two length elements at equal distance from P. Like this is A and this is length element B. The length of each element is dl and corresponding charge is dq. Now the electric field intensity, and first of all we calculate the direction of electric field intensity. So we produce this. If this angle is theta, then this angle will also be theta, because alternate angles are vertically opposite angles are there, and if this angle is theta, then this angle will also be theta. This is the direction of DEA, electric field intensity due to length element A, and this is DEB, electric field intensity due to length element B. Now we resolve this into components, and here the cos component will be there, DEB cos theta, and here DEA cos theta, here DEB sin theta, and here DEA sin theta. We know that DEB sin theta and DEA sin theta are equal in magnitude and opposite in direction, because theta is equal, length element is equal, so DEA and DEB are also equal. So because they are equal in magnitude, opposite in direction, so they cancel out, and these first components of electric field intensity DEB and DEA are along same direction, so they add up. So we conclude that due to a uniformly charged conducting wire, electric field intensity due to positively charged will be along this direction. For positively charged particle, perpendicular and away from the wire, and for negative charge it is towards the wire. So this is the direction of electric field intensity. Now we shall discuss about the magnitude of electric field intensity. We have discussed about the direction of electric field intensity due to uniformly charged wire. Now we shall discuss about the magnitude, and for the purpose we again consider the wire of a length, corresponding charge is Q, and the distance is R, P is the point. Now we consider a cylindrical Gaussian surface of radius r and length l. This is the P. So there are three surfaces in electric field in this Gaussian surface, and the direction of electric field intensity will be vertically outward direction. So for this surface S1, the direction of S1 will be perpendicular to the surface, and electric field intensity will be along this direction, and both are perpendicular. For the surface S2, the direction of S2 will be this, perpendicular to the surface, circular surface, and electric field intensity will be perpendicular to the wire, and they are also perpendicular, means 90 degree. And now at point P, means curved surface, just like that, this is the upper surface, circular surface, this is lower circular surface, and this is the curved surface. And for this curved surface, electric field intensity E and the surface S3 are along same direction. So consider a wire of infinitely long straight, uniformly charged. We consider its L length and Q is corresponding charge. Q is corresponding charge, and we also consider a cylindrical Gaussian surface of a length and R radius. Then from Gauss theorem, we know that the Gauss theorem is integral for closed surface integral E dot dA. Corresponding flux of Gaussian surface is equal to summation Q, the ratio of algebraic sum of all charges enclosed by the Gaussian surface, that is summation Q upon epsilon. For the air we consider, or for vacuum we consider epsilon naught. Now the whole surface is divided into three surfaces, S1, S2, S3. So integral S1 E dA cos 90 plus integral S2 E dA cos 90 plus integral S3 E dA cos 0. Here for surface S1, the angle between surface and electric field intensity is 90 degree, because electric field intensity is always vertically upward direction or perpendicular to the wire, and in this case it is also perpendicular, and in this case it is 0, and the charge enclosed by the L length of the wire will be Q upon epsilon. For surface S1 it is 0, for surface S2 it is also 0, for surface S3 E integral dA is equal to Q upon epsilon naught E into the area of curved surface, and area of curved surface is 2 pi r L. 2 pi r, this is the 2 pi r, the breadth, and the length of a cylindrical surface is L. 2 pi r L is equal to Q upon epsilon naught E is equal to Q upon 2 pi r into L into epsilon. Q by L, we know that lambda. So E is equal to lambda upon 2 pi epsilon naught into R, and if we multiply and divide it by the 2, then this value becomes 4 pi epsilon naught, and 1 upon 4 pi epsilon naught is equal to K. So 2, this 2, K means 1 upon 4 pi epsilon naught, 2 into 2, 4 pi epsilon naught, lambda upon R. This is the electric field intensity, and if E is, in this case, E is inversely proportional to R. So if we draw the curve between E and R, it will be hyperbola. And for the curve E and 1 upon R, it will be a straight line. For greater value of lambda, if we discuss this value, this is the form of y is equal to m into x. Here y is equal to E, m means 2k lambda, and x means 1 upon r. So this is a straight line. Means for a vacuum, the slope of the curve will be greater. For the greater line charge density or linear charge density, the value of slope of this curve will also be greater. And I shall draw these curves at this point here. E, this is E and 1 upon R. This curve and this curve for vacuum, because it has greater slope, because value of K is greater. And this is for a medium, because value of K for a medium is smaller. So greater is the value of K, greater will be slope. Smaller is the value of K, smaller will be slope. And the second case, if we draw the E and 1 upon R, two curves will be there. This is lambda 1, this is lambda 2, and in this case lambda 1 is greater than lambda 2. We can imagine that E is equal to 2k lambda into 1 upon R, and this is y is equal to Lx. M slope of curve means m is equal to 2k lambda, 2 is constant. So if k is greater, then slope of the curve will be greater. If k is smaller, then slope of the curve is smaller. If the linear charge density is greater, then the slope of the curve will be greater. And if linear charge density is smaller, then the slope of the curve is smaller.